Hello, everyone that's here already. Thanks very much for coming today. My name is Jordan McKenna, and I'm with the impedance support team. And today we have a presentation that was created by Dr. Anshu Verma. So thank you, Anshu, for these slides. And we are going to be talking about detecting plasma arcs and optimizing post-RF performance in semiconductor tools. So I'll just give another minute or two, let everyone join. But yeah, what I should say is that this is recorded. So if anyone needs to leave early, absolutely no problem. Just we will send the recording out to you after it is all done. I think it will probably be tomorrow. And if you have any questions during the webinar, unfortunately, everyone is muted, but there is a Q&A section. So if you want to just type in the questions as they come to you, and towards the end, we'll leave a bit of time to answer those. So thank you very much. Just another few seconds. We will carry on. So hey, yeah, let's get started. So what are we going to talk about today? So arcing and issues within an RF and plasma environment. So what is arcing? What are the main causes of arcing? And the main thing, what to avoid, and rules of thumb when minimizing arcing happening within a plasma environment. We will also be talking about the impedance technology for arc management, so our Alpha VI probe. And with that, we can show arc detection with the Alpha probe. And today we also have a live demonstration of this arc detection in practice. Secondly, we will also be showing pulsed RF monitoring. So we'll also show a live demo of the Alpha for pulsed RF monitoring. So the way we're kind of going to do the webinar is split into two sections. First, we'll look at arc detection, what causes it, and show the live demo. Then we'll come back to pulsed RF monitoring and then show that live as well. So to dive right in, the Alpha is one of our VI probes. What that means is our voltage current probe, which is put in the RF line. Now we have a wide range of products, and if there's anything here that catches your eye, let us know. We can talk about that on another date. But today we're just going to be looking at the Alpha for arc detection. So arcing events within RF plasmas. So what is an arc? To, I suppose, visualize it for anyone who hasn't seen an arc or doesn't know what an arc is best way to think about it is a mini bolt of lightning that happens within your plasma tool. So arcing is most often results from charge buildup and eventual electrical breakdown on the surface of dielectric films deposited on the target and chamber walls during sputtering and deposition. There are many reasons for arcing in RF powered systems, including charge buildup across the gate electrode patterns on semiconductor wafers and polymer coatings on chamber surfaces. Other factors include defects in the reactor or chamber hardware, degradation of protective chamber ionization layers, differences between electric potential across different tool parts, or simply just the magnitude of the RF power itself. And here we have a couple of examples of what arcs actually look like inside the tool. So here we can see some degradation on the anodized walls, or here on the actual wafer itself. So what are the main causes of arcs? We're going to dive into three common causes that typically we see in the semiconductor industry. And the first one here is poor chamber seasoning. If the chamber seasoning is incomplete, then some areas of the wall will be conducting while other parts are insulating. Or if the coating is uneven, then some areas may be thin enough for breakdown to eventually occur through the dielectric material to the wall. This type of arc is responsible for particle creation. So what occurs is we have aluminium particles sputtered from the aluminium chamber wall, and these metals cluster and collect electrons, becoming super negative ions. Then these particles just collect above in the plasma sheet, and they sit there until the plasma is turned off. And then as soon as the plasma is turned off, they fall into the wafer and they contaminate the next layer. An example of this is during a plasma-enhanced chemical vapor deposition chamber with poor seasoning. They took them multiple dummy wafers before it was allowed to run product. So the chamber until the chamber become correctly conditioned. So if we look here, in this kind of diagram, we see it's stable, stable, and we get this kind of spike in voltage where it changes from about 50 volts to about 35 volts maybe. And this can happen, it's very common, and there's a few possible solutions for this. One is just to increase the duration of the seasoning step so the chamber is well coated. This may require an increase in the cleaning step duration. Another is to introduce a pre-seasoning step like an extra cleaning process. This especially needed after the chamber has been opened and there may be some water vapor inside the tool. And the last instance is to purge the system of leftover metal particles by putting in a dummy wafer and run a high glass flow for a few minutes. So taking our example, which we showed here for the PECVD chamber, if they had just kind of run high gas flows for a few minutes with the dummy wafer, this will kind of purge the system of all the particles, and anything remaining when it was turned off would land on the dummy wafer. So this is, if you have poor chamber seasoning, some steps for preventing arcing in this kind of scenario. A second common cause is poor grounding. So a poor chamber chassis to earth connection will cause the chamber to float to a certain voltage near the plasma potential, and this can cause unpredictable plasma behavior, including arcs. So if we look at our diagram here, we can see we have a little bit of stability and then lots and lots of arcs occurring. And then again, we repeat the cycle again and again and again. Another cause is poor wafer contact with the chuck or poor wafer clamping. And this is particularly critical when a conducting layer is being deposited onto an insulating layer. Charge will build up on the insulating layer until it breaks down to the nearest conducting surface, which is sometimes through the lower layer of the wafer itself. So how do we prevent this? It's kind of simple. We just need to be aware that invisible oxide layers may build up on metals in the chamber. So connections to the ground should be scrub free of oxides, and RF travels on the surface of materials or its skin depth. So cleaning the surface ground connectors before attaching them is essential. One final piece is to check the braiding for damage and replace if necessary. And our final common cause of arcing is actually to do with the generator and the matchbox. So arcs can be caused by faulty parts in the RF network. So one example that we're showing here is when products had burn marks if they were left in the tool for too long. So if the process was finished, they were left in the tool for a couple of minutes and then taken out, then they were seeing these burn marks. However, if they were taken out immediately, there was never any damage. Now, the reason for this is it was discovered that the generator was randomly outputting power even when the dial was zero, and this was due to a faulty relay switch. So during this off period, we have a closer look here, and you can see, if I zoom in a little bit, we have the voltage actually spiking to about 3000 volts, and we have this ringing effect. Now, ringing is a common thing we see if there's something faulty in the RF line, say a faulty relay switch or matchbox capacitors failing. So they give this kind of oscillating shape. So they are three of the main causes of arcs in the tools that we've seen. And so one great thing is to have a couple of rules of thumb before you do any sort of processing. First one, as you mentioned at the start, arcing will happen at the interface between insulating and conducting materials. So poor chamber seasoning can cause this. Beware of coatings. Arcing will also happen on rough surfaces. Pitting is common, especially on some ceramics or quartz stones. So run a glove finger along the ceramic, and if it feels somewhat rough, then replace. And finally, as we mentioned, poor ground connections cause arcs. Remember, if the chamber is moved, to connect it back to ground. For RF, surface ground planes work. Wires with a single contact point do not work. So those are kind of the main causes of arcs that we see typically in semiconductor processes. But what does an arc actually look like? Well, here we've pulled some data from our impedance alpha software. Arcs are unpredictable, then they're often not detected until the product is already damaged and destroyed. It may not be too obvious that arcing occurs because they can be nanoseconds long, and this happens so fast, standard tools just don't catch them. They can have many different causes depending on the type of chamber and chamber plasma processes. Apologies. So the solution for one chamber may not be the solution for another chamber. So how do you prevent this? Well, having the ability to check the tool for arcs is the first step in controlling. If we zoom in here, we can have a look at what this arc looks like. So a top left graph, or top right graph, apologies, has what we showed before with this spike down. But with our impedance alpha software, we can actually click on this event and see this arc happening over a 5 millisecond window. If we look at the actual arc itself, we see this big sharp drop down and recovery after about 350 microseconds. And then after about 2 milliseconds, it kind of goes back to normal. This is what a typical arc will look like. It's just random voltage spike, usually downward. Arcs can be categorized as either macro or micro. Micro arcs usually last tens of microseconds and cause relatively small voltage changes, and macro arcs can be up to 500 microseconds to milliseconds long, and they can be large voltage and current disturbances. Now, I know what you're probably thinking. You're saying, Jordan, you just said arc can last for nanoseconds, and your tool is showing it in milliseconds. Well, the Alpha can get up to a 1 microsecond resolution. And the advantage of using the Alpha tool is because it has this 1 microsecond resolution. And even if an arc lasts a couple of nanoseconds or hundreds of nanoseconds, the disturbance to the plasma will last a lot longer. And this disturbance to the plasma is actually what the Alpha is measuring. So we'll jump into that a little bit later. So we've talked a lot about the alpha, but what is the alpha? The alpha is a radio frequency RF event detector designed to monitor short-lived, unexpected events in RF and plasma. It monitors things such as arcs, ignition phenomena, instabilities, and it can also measure pulsing with a 1 microsecond resolution. And so it is a single frequency sensor suited for inline for measuring voltage, current, and characterized event count. Now we'll jump into characterized event count while we're doing the live demo and explain just how we characterize these events. So the features of the Alpha, it is suited for a pre-match configuration. And what that means is it sits between your RF generator and the matchbox, or within the 50 ohm region. The advantage of this, I suppose, is there is a lot of opportunity to put a tool between the generator and the matchbox. Almost every tool will have a bit of cable here, and so having an Alpha situated here, absolutely no problem. The other advantage is once it's there, you don't have to move it, and you can record events every hour, day, week, month, year, whatever it may be. You can just leave it there and collect events non-stop. So we'll jump into a little bit about the specs in case this is something that you are interested in. So we spoke about it being 50 ohms. As you can see here, the Alpha has typical QC connectors. Now this one is an N-type female, but we have a variety of options. So B6N, 7/16 that can all be QC or quick change. And these typically go to about 12 kilowatts power. But if you're going slightly higher power than that, we do have higher power options available with 30 kilowatt and 90 kilowatts. The way it communicates is over the network. So we have Ethernet and EtherCAT communication capabilities. And the advantage of this is you can just hook it up to the network. You don't need to be anywhere near it. You can have the Alpha in the lab, and you could be at home detecting events. The Alpha report rate is about 10 samples per second, while its sample rate is about 1 microsecond. And the onboard storage, so storage without actually uploading to the network, is about 14 hours of data, or about 5,000 atypical pulse or arc events. So how does the Alpha actually work? Well, if we jump back here and have a quick look at it, the Alpha is typical to all our VI probes that go inline. And the way this works is where the connector sits here, there's one on the other side, and connecting the two, there is an RF rod. Now, what we mentioned at the start is RF travels skin depth or on the surface, and above this RF rod, we have what we call a pickup board. On the pickup board, there is a capacitive and inductive loop. And using those, we are picking up electric fields and magnetic fields, and then converting this into voltage and current. So by digitizing these voltage signals with a 32-bit integer ADC, this goes into an FPGA, and then we can pull out data which we looked at earlier today. But how does it characterize these events? Well, the Alphen has, as we mentioned before, a sample rate of 1 microsecond and a report rate of 100 milliseconds, where it's detecting any significant changes in voltage or current. What we have here is kind of a small little diagram showing an E11, an E21, and E33. And basically, this is the way the Alphen will characterize the events. So you can see E11 here only changed by 1%, E21 changed by -3%, and E33 changed by about 5%. And so the real advantage, I suppose, of the Alphen is that you can change these classifications. And so what may be an E33 during one process may be an E11 on another. And so you have the power to change what you consider to be an event or not an event. And then again, just to reiterate, the Alphen is compatible of working over the network. I suppose the main advantage here is there is software which we'll be showing today during our live demo, but there is also a web interface where the data is consistently just uploaded. So if you wanted to communicate and I suppose have the Alphen communicating with your tool, let's say if we see one of these E33 events you want to shut down, then we have some scripts that we can pull, some Python examples or API examples, I should say, and we can pull the data and just can communicate them with your tool. But how do we collect the data or how do we classify these events? So the Alphen software is equipped with a recipe configuration menu. A recipe can have multiple steps and enable for different processes to be monitored within the same run. Each step can be altered, as what we mentioned before. An event for one process may not be an event for another. Anytime an arc happens, then it'll be characterized depending on the amplitude and duration. And that's where the E11, 21, 33 all come from. And after that event occurs, this microsecond resolution data will be sent to our software for viewing, and the event will be highlighted in the real-time data. So if we have a quicker look here and we look at this kind of array just here, we have our event amplitude. So let's just take voltage, for example. If it changes by 10%, but only lasts about 50 microseconds, that's what we call an E11. But let's say we have something that lasts 500 microseconds and the voltage changed by 50%, then that's our E33, that may be our alarm shutdown. And one final thing to mention just on how the Alphen works is the data filtering. So RF can be slightly noisy, as we know, so we don't want to be picking up what we call false events. So to do this, the Alphen takes in the raw signal, which is here in gray, and it takes a certain window or a noise filter, low pass filter, to remove these false detections. So during this 32 microsecond window, the signal is filtered and gives this average signal. So then when a real event occurs, we know it's an actual event and not just noise pickup. Perfect. So once an event occurs, you can then view it in the impedance software. As you can see here, this is just a clip from 2016. So you can go back however many years you want, click on the day you were running it and have a look at what was occurring. Then you have an event shown here by this symbol. So if we look just on this right-hand side, you can see all the different shapes and classifications for these events. So these were E33 events. So by clicking then on this, we can have a look at what the event actually looked like in that 5 millisecond window. Okay, so I talked enough about the Alphen. So I suppose now is time to actually show you it in action. What we're going to do first is I have an Alphen set up in the other room with a small amplifier. And first, we're just going to put in a continuous 13.56 signal and try create some events. So I'll just escape out of this. Let me know you can still see my screen. So here's the Alphen software. Lovely. If we want to connect to a sensor, what we need to do first is create a session. We create a session here. We're going to Alphen demo, and I'm going to create a new one. I was obviously doing a little practice earlier. We'll call this one demo 2. And just so we can kind of create it from scratch. Let's save that. Okay, now we've got our session and we can connect the sensor. Now, we have this capability. So first thing I should mention is configure sensor through IP, or configure sensor IP through USB. If you click this, then you can change the IP address of the elephant to suit what you want. As the elephant is in the other room, I am not going to be able to configure the sensor to show you, but what I can do is scan the network and have a look for it. Now I know that this is the IP address of my elephant and that is the serial number. So if I double click this and connect, then press OK, we are going to have our sensor come up. Now it's going to be pulling up all the data that's been going on for the last while. So what I'll do is clear incoming data and we can just continue on. Perfect. And what I'll do then is switch on the amplifier, and you can see here we had a bit of a strike event. So actually, before I do that, I'll switch this off and we'll just run through the recipe first of all. So we're connected, we're running, happy days, but let's have a quick look at the recipe configuration. So if we want to create a recipe for a process, let's call it process 1 and step name A. Then we are creating this recipe, which can have multiple steps. So if you have a cleaning step, if you have an etching step, deposition, they can all be put within the same process 1. For now, we're just going to do a singular step recipe. Let's make the step duration 2 minutes, and we are using 13.56. Skip time at start, absolutely fine. And here we have our minimum event amplitude and our maximum event length. So we can leave this as is, and this will be what characterizes our events. If we add step here, I suppose jump over here. This is the noise filter length. When we were talking about the filter, we can increase this filter length. So let's say you are still picking up maybe an ignition event, even though you're skipping the time at start. Then you can increase the noise filter length to prevent this ignition maybe from being seen, or if you have particularly noisy tool, then you can also increase this noise filter length. The RF on off switch time is very useful, as sometimes during a process you may have an off time, but you may want to keep everything within the same run. So by putting this off time longer than your actual real off time, then you can ensure that everything happens within the same run. Snapshot is a functionality on the Alphin, because you have all these classifications for events, but maybe you want to see what it looks like when it's working well. And so being able to snapshot is essential sometimes. You can manually snapshot by pressing the snapshot button up here, or you can have an auto snapshot which happens at certain intervals. We will look at doing that later, but for now we'll just keep it off. And then we'll jump into pulsing later as well. So let's add this step, step A. We'll save the recipe, okay. And let's right click here, select that recipe, load the recipe on, process 1, open. Cool. So now once we start the RF again, we should see a new run begin. Perfect. So nothing too exciting. We have our 13.56 megahertz coming through. No events to be seen yet. We have our voltage being measured and our current being measured. And then this is when we're pulsing, so we can jump onto that a little bit later as well. What I'm going to do now is try create an arc by quickly changing the amplitude. Because I don't have a way to physically create an arc because I'm not connected to a chamber, I'm going to try this. Let me go to amplitude and okay, nope. I didn't get an arc there. So obviously I'm a little bit too slow at changing the amp. Oh, I got one there. Perfect. And we can have a closer look at that event there. I will try do it again. Maybe if we have it on a new run. Let's go. And what we can do just to ensure that we see an event is recipe, because it's not the best for actually creating arcs, what we can do here is enable strike event. What that does is we can actually see when the strike or when the ignition occurs. So let's confirm edit, save that. Okay. And I guess must be process one. Okay. So let's start it again. Oh, and we get our strike event. Perfect. Obviously, I'm not quick enough, unfortunately. No. Well, that's absolutely fine. What we can still do is look at that strike event. Oh, and see here, you can see when the strike occurred, and we're seeing that event occur. So great. So that is how it detects arcs. Obviously, I couldn't create arcs today. I'm going to give it one more go crazy. No. Okay, no worries. So obviously I'm too slow, and I'm not creating real arcs, so it's not detecting. So that is the arc detection. What I will do next is jump down onto the pulse RF monitoring. So let's go back to our webinar and slideshow. Let's turn slide. Okay, so pulse RF monitoring. So the Alpha BI probe for pulse monitoring, it has two onboard algorithms that constantly process RF data. The first is designed for detecting arcs within a plasma, and the second monitors every single RF pulse and checks that each pulse is within spec. So when you're doing pulse monitoring, you are essentially looking to see, is every single pulse the same? The Alpha can check the pulse for the correct on time, correct cycle time, and counter reports what we call bad pulses. So if your pulse has an incorrect period, incorrect duty cycle, it will show up in the Alpha as a bad pulse. So duty cycle deviations directly correlate with the number of wafer defects outside of a certain acceptable window. So similar to how we have an acceptable window for what we classify as an arc, we can also have a window for what we classify as a bad pulse. And again, we can use the snapshot function to look at our good pulses and our bad pulses. So how does the pulse monitoring system work? When the voltage or current surpasses the signal base threshold, the pulse is then captured. Every pulse should have a stable period and duty cycle, as we mentioned before. But using the impedance software, we can set limits as to what we consider to be correct. And if a pulse goes beyond these limits, that is our bad pulse. So let's say in our ideal scenario, we have this perfect square wave. If our duty cycle is somewhere, let's say 30%, and it's here, it will be considered a bad pulse. Similarly, if you have a period, let's say it's 1 kilohertz, and then we have a period maybe 1100 microseconds, then we will see that as a bad pulse also. But how does a pulse really look? Now, this is a little bit of an exaggeration, but it's a good, I suppose, visual example. So in practical applications, a pulse will not be exactly perfectly square. It'll be relatively square, but not perfectly. A lot of the time, they'll have an initial overshoot, which has a pulse on maximum, and then this rapidly decays to pulse on average. And then at the end, we'll also have a small lower part where we have a section for discharge. The impedance snapshot function can capture these pulsing characteristics, even if it's not a bad pulse. Now, with actual pulse, you will see absolutely this overshoot, but realistically, I suppose the minimum would be somewhere near the center, because what's happening, you have this overshoot, and then it's trying to match to that 50 ohms, and by the time it's matched, then it's off again. So that's more realistic of what a pulse will look like. But one thing is, how does this, I suppose, why does this matter? Well, let's talk about high power applications versus low power applications. If we're in a high power application, then a large overshoot can actually result in arcs happening within the tool. So it's important to understand this max pulse voltage, as it can unknowingly cause wafer defects. Similar, let's flip the switch, and if we go to a low power application, if the overshoot is not large enough, then plasma ignition may not occur. So understanding controlling the pulse overshoot will result in better process repeatability and less wafer scrappage. Another thing to mention is if the pulse, I suppose, period or pulse duty cycle is not correct, then the ion energy and ion flux will also be incorrect. And so this also goes towards wafer defects. So how do we control this overshoot? Overshoot can be controlled by adjusting the slew rate. The slew rate is essentially the time it takes for the pulse signal to reach its pulse on max, or similarly, the time it takes to get to its off time. By increasing the slew rate, the overshoot will decrease as there is less displacement current due to slower rise time. Similarly, decreasing the slew rate will result in a larger overshoot. The alphin, while it can do on-off pulsing, can also do multi-level pulsing, which we will show in the demo today. I couldn't get a good act for us, but I will be able to show good pulsing data. So I suppose let's jump into that. Cool, because this is open. Right. So yeah, we're still running away. So let's turn this off for a second and go back to our recipes. So I'm going to load in, as they say in the cooking shows. Here's one I prepared earlier. And yeah, this is pulse event 1 kilohertz. So this is for a typical on-off pulse. And so the only, I suppose, addition here is this section is now enabled. So what we have is the pulse frequency, the pulse duty cycle, and then our error margins. So you can see here, we actually have our error margins quite narrow. So hopefully all goes well. And then also our resolution as 1 microsecond. So let's save this recipe, absolutely fine. And let's load it in onto the tool. Pulse event 1 kilohertz, perfect. Yes, please. So while we are running, this is running. So let's turn this off for a second. And what I'm going to do is modulate the 13.5 signal with a square wave. This square wave has a 50% duty cycle, like our recipe says. And yeah, let's get it going. So we started our new run. As we can see here, the voltage has dropped quite dramatically, as we're only half time on. And so firstly, let's take a quick snapshot of what our thing looks like. We'll stop scrolling here and take a quick look. And as you can see, here is our pulse signal. Now, if I change the AM frequency to be, let's say 990 quickly. Oh, maybe that was a little bit too long. Once the alpha is here flashing, it is actually uploading all the different events. Because I was a little bit slow off the mark there, seems to be the theme of the webinar, I created a lot of events within that time. So I do not care about all of them, so let's clear the incoming data. We already have lots of data here. And so if we click on one of these bad pulses, we can see here our period is completely different to what we had for our good pulses. And the advantage, I suppose, of that is we can then compare when we have our good pulses and when we have our bad pulses. And you can see here, just in that quick second, I created a lot of bad pulses. Let's, I suppose, show or I should jump into and talk about this. So you can see here, it is showing what the actual pulse frequency is, pulse period, number of pulses. So this is all to do with the pulse. When we're in slot 1, it is just your on-off or 2-level pulse. So you can see here duty cycle, we can see our average voltage, our max, and our min. When we introduce multi-level pulsing, which we'll do now in a second, our slot 2 will come in for the second level. And yeah, so I suppose let's change it up. So we'll turn this off. And we will select after recipe, load. And again, here's one I prepared earlier. So I will show you what is going on here. Oh, apologies. Load recipe. So here is our multi-level pulse recipe. So one addition here is our multi-level pulse threshold. So we have two thresholds. One I should have mentioned earlier, so let's go back to that. If we right-click here, press configure, we have a signal-based threshold. And so what that means is as long as the signal is above 2 volts in this instance, then it will detect an event. In our recipe for our multi-level pulse, we now have a multi-pulse threshold. So the multi-pulse threshold is the difference between the high and the low pulse. So you kind of want it to be in between. And that's how the software knows that this is where my level change is occurring. And similarly, we have our pulse duty cycle. So what I have coming into this is a high, low, off pulse. And so the duty cycle is 66%. So let's say that that's absolutely fine. And let's turn on the modulation. Okay, so let's get this going. And what we have here first is a snapshot, so an auto snapshot. And then we can, I suppose, have a quick look at that. Here is what our multi-level pulse looks like. So you may have noticed during the recipe, I had set the threshold to be, the multi-level threshold to be 6. And this is because it's the level here between the high and the low. So if we do what we did earlier, where we change the AM frequency just quickly, we should get a lot of events occurring in that short space of time. So just catch up there. Perfect. And you can see here now we have a lot of different events. So if we click on that, we can see here the duty cycle is completely changed. Let's see if we have another one. Okay. Yeah. So you can see here we have a lot of kind of incorrect pulses there. And I suppose one advantage of this is we can add this event to an overlay. So this is one of our bad pulses. And let's put our good pulses. Oh, add events to overlay. Oh, sorry, I put the wrong one in. And then we can have a look at our events overlay and see how much they differ. So you can see here we have our good pulses and then our bad pulse. I'll try and pull out another bad pulse. Looks a little bit worse. Add events to overlay. Okay, okay, perfect. Okay, cool. And so that is the simplicity of it. And now you can see we have our slot 2 enabled also. Yeah, so that is the Alpha software showing the pulsing, but I know what you're thinking. You may not have time or resources to go into the software, click on every pulse, overlay them, absolutely no problem. Well, what we can do is put in our IP address that we have to the network. If we just put in the IP address of the sensor, then we can just look at, I suppose, the Alpha test page. Now, if we put in, I suppose, /service data.cgi, now we can see the actual live data of what's occurring on the Alpha. And if we refresh this, it's going to be changing consistently again and again and again. And so the advantage of this is you can just pull this data and connect it to your tool. So you can have these alarms set up for when a bad event, let's say lots of pulse events occur or an E33 event occurs, then we can have this connected to your tool to put on an alarm or switch off period. So let's go back to this. That's our current slide, switch. And yeah, so we kind of covered a lot there, and I know I kind of spoke a lot, but I suppose, why is this important? Why do we care about events? Why do we care about arcing? Why do we care about pulsing? So for 7 nanometer, 5 nanometer processes, the repeatability of the pulse characteristics is critical. I mentioned this a little bit earlier, but incorrect pulse and periods of duty cycles means differences in ion energy and ion flux, which lead to defects on the wafer. Also, macro arcs are one of the lead causes of unnecessary wafer scrappage. The truth of the matter is, arcs will happen, especially in metal deposition processes. But the key is to know when arcing will become detrimental to the end product. Using the Alpha tool to plan a scheduled maintenance once arcing goes beyond a specific threshold will ensure for overall better yield. So what I mean by that is if you have the Alpha tool just sitting there and recording arcs, what could be okay is a lot of these E11 events for a long time. But let's say they start becoming E21 or the amount of arcs actually increase over time, then it could mean scheduled maintenance to ensure that the chamber is kept in good condition. As we mentioned at the very start, chamber seasoning and oxide layers, all that good stuff. So in summary, we covered what an arc is and what are the most common causes during RF plasma processes. We had a look at the Alpha technology for its high resolution process monitoring. We got to see the Alpha in action. Now, this was just single generator to an amplifier to a load, so not a whole lot we can do, but we do have some better examples. I'm going to show that now at the end. And planning scheduled maintenance on the tool from a better understanding of major events. So if we, I suppose, jump back to the software, while we had these good events, let's show it on an actual tool. So if I load in the session, and this is the advantage. So this was taken years ago. Let's have a look. Events 2018. We can still go back and have a look at this. And we'll look, it was the 6th. Perfect. And let's just, oh, apologies. And let's just have a look at this. So this is typical process. So you can see here during the first process, there was some this was like a seasoning process, and you can see there's a lot of events happening here. Then during the second process, we got one major arc. If we have a look at this, this is what a real typical arc looks like. You've got this spike down and then settling period before it goes back to normal. And then over time, then you can see the process changed and a lot of arcs occurred again. So even just being able to go back, pull up this data and see what happened during the process, which step in the process, and how detrimental it was is vital for processes. So yeah, that is everything, I believe. So yeah, current slide. So us at impedance, you probably know who we are, but we are trying to do cutting edge plasma monitoring. Today we spoke about the Alpha, but we have a lot of other tools which we constantly do webinars. I believe it's once a month. So if you are interested or if you enjoyed this webinar and want to see any others, they are available on our website. Thank you. I will now, I don't know, there's a couple of questions there. So let's kind of jump into the Q&A. So we have a question from Making Fan. So in 2 seconds. I'll just pull the questions over here, so we're not seeing it. Yeah. So, should it be fitted to an ICP source or a CCP source, or both if both sources are used? Well, I suppose the truth of the matter is both will work. The sensor works by looking at the plasma impedance. So both the ICP and CCP side will see it. When in doubt, choose the CCP since the way for health is more important. Yeah. One other thing is for every process, if bias is used, then put it on the ICP, or if both are used on or off, then both should have a sensor. So you can put one on each if you want to monitor both at the same time. Yeah, so either or, but typically CCP. What is the detector bandwidth? Can it work with variable frequency RF generators? Yeah, it can work with frequency generators. So what it has on it, the way the sensor works is it has either 10% or 2 megahertz, whichever is smaller. So above 20 megahertz, the bandwidth is 2 megahertz, but below that, then it's 10%. So that is the bandwidth there. Usually there's RF current or voltage monitoring tools available, also from impedance, I believe. So what is the difference and our benefit of using the Alpha? I suppose the key benefit, which we mentioned, is the 1 microsecond onboard data processing. for high resolution monitoring. So if you are trying to use the typical arcing, they may not see these kind of very quick arcs that are happening in the space of nanoseconds. Like other than the other sensor, like the octave sensor, has very high power and impedance measurement accuracy, and it has 1 microsecond resolution as well. But it's not like the Alpha where you can see this instant event happening. I suppose, yeah, that's everything. I don't know if there's any other questions, or if not, we can leave it there. What's the difference between alpha and mixed? What's the difference between alpha and mixed domain oscilloscope in terms of measuring RF pulses, measuring IV characteristics of the plasma? I'm not too sure on that one, sorry. So the question is, what is the difference between alpha and mixed domain oscilloscope in terms of measuring RF pulses and measuring IV characteristics of plasma? I suppose the main thing would just be convenience of the tool. It can sit in the 50 ohm region and it can just be put in line. I suppose is the main difference there. Hope that's okay. Usually there are voltage current monitoring tools also available. Yeah. I think that there's, I suppose another thing I just thought of there is the difference there between the alpha and an oscilloscope is, you know, the snapshot that we spoke about earlier, you can kind of just click snapshot and look at it there live, and then you can overlay these results rather than having to pull the data from an oscilloscope. So I suppose that's quite easy as well. I think I've covered all the questions. But hey, if you've any more questions or you think of anything after, let me know. You can always come back. You can email support@impedance.com. You can see the email here, and we'll get back to you straight away. So I suppose we can leave it there. Thank you very much, and thanks for coming.